used to make semiconductors. In order for silicon to turn into a semiconductor chip, it needs to go through the essential processes of wafer manufacturing, oxidation, photolithography, etching, deposition and ion implementation, metal wiring, EDS, and packaging. Let's take a closer look at these processes. Semiconductors are stacked high and solid to form a complex structure similar to a high-rise building. Constructing a building starts with the foundation. A wafer is the foundation for the semiconductor. Most wafers are made of silicon extracted from sand. How can these tiny grains of sand become a wafer? First, sand is heated until it melts into a high-purity liquid and then gets solidified by crystallization. The resultant silicon rod is called an ingot. These ingots are sliced into a disc, thinly sliced wafers. The surface of sliced wafers is rough and contains defects, so polishing machines are used to polish the surface of the wafer. The reason is that defects on the surface could negatively affect the precision of circuits. If you look at a photo of wafers, you can see a grid pattern on the surface. Yes, the word wafer comes from biscuit wafers. A wafer made this way is the main material for semiconductors. Because the larger the diameter is, the greater the number of chips that can be produced per wafer is. So, the diameter of wafers is becoming larger. Because the resultant thin disc-shaped wafer is not conductive yet, a process to make wafers semiconductive is required. First, wafers go through the oxidation process. Oxygen or water vapor is sprayed on the wafer surface to form a uniform oxide film. This oxide film protects the wafer surface during the following processes and also blocks current leakage between circuits. The film acts as a strong protective shield. Now, the foundation is ready. The building up process begins. Just as you draw blueprints to build a building, you draw a circuit design onto a wafer, which is called the photolithography process. It is called photo for short because it is similar to developing a photo taken on a film camera. With semiconductors, a photomask functions as the film. A photomask is a glass substrate with a computer-designed circuit pattern. In order to draw the circuit on the wafer, the photoresist, a material that responds to light, is applied thinly and evenly on the oxide film previously placed on the wafer. Now, when light transfers the pattern photomask, the circuit is drawn on the wafer surface. Just like developing a photo, a circuit pattern is imprinted on the wafer by spraying developer and removing unlit areas from the areas that are exposed to light. After an inspection of the wafer to check whether the pattern is drawn well, it moves on to the next step. Now, unnecessary materials are carved out so that only the design pattern remains. Using a liquid or gas etchant, unnecessary materials are selectively removed to draw the desired design. When chemical solutions are used for etching, it is called wet etching. And when gas or plasma is used, it is called dry etching. We will talk about these details in the future. Let's imagine constructing a building on a semiconductor chip smaller than a fingernail and thinner than a sheet of paper. The photolithography process and the etching process are repeated several times on the wafer, layer by layer. Here, an insulating film that separates and protects the stacked circuits is required. It is called a thin film. Coating the thin film at a desired molecular or atomic level onto a wafer is called deposition. Since the coating is so thin, precise and sophisticated technology is required to uniformly apply the thin film on a wafer. To give the semiconductor electrical characteristics, ion implementation is also required. A semiconductor made of silicon does not conduct electricity, but adding impurities, it conducts current and has conductive properties. In summary, through the wafer manufacturing, oxidation, photolithography, etching, deposition, and ion implementation processes, the wafer becomes conductive and numerous circuits are drawn on it. Now, in order for this circuit to work, an electrical signal must be applied. It is necessary to create a path for electricity to pass through according to the circuit pattern. This process is called the metal wiring process. It is a process that allows electricity to flow by depositing a thin metal film using materials such as aluminum, titanium, or tungsten, so that electricity can pass through the semiconductor well. The chip manufacturing processes are now coming toward completion. The next step is EDS. This is the process of testing to ensure flawless semiconductor chips. In other words, it is a testing step to sort out defective chips. Yield is a percentage of prime chips relative to the maximum chip count on a single wafer. The semiconductor chips selected through the EDS process are made in a form suitable for devices. This is the last process, the packaging process. The wafer completed through the previous steps are cut into individual semiconductor chips that can be loaded on an electronic device. An individual chip must have a path to exchange electrical signals with the outside and have a form to protect it from various external elements. The wafer is cut into individual chips, and the diced or sawed chips are placed on the PCB board. In the bonding step, the contact point of the semiconductor chip placed on a substrate is connected with the contact point of the substrate. Then, molding finishes the chip package to its desired shape. After sealing the semiconductor and labeling the product name, the semiconductor chip we commonly see is completed. Of course, only after going through the final test will it become a finished product. Today, we learned about the essential processes that produce semiconductor chips. These complex processes can be separated into the pre-process up to the wafer processing stage and the